Hello everyone, my name is Victor, and in this video we're going to do a comprehensive review of the substitution and elimination reactions. This is going to be somewhat of a long one, so go ahead and grab a cup of tea or a coffee, your favorite notebook, and let's get started. So the substitution reactions, SN1 or SN2 reactions, is going to be a type of reaction we're going to be replacing something inside of our substrate with something else. So suppose I have this molecule as my starting material, 2-bromopentane. Oh, and by the way, if you don't remember your nomenclature, might be a good idea to review that, because I can guarantee that the final exam or probably your next midterm is going to have that. Anyways, so my 2-bromopentane is a good example of an electrophile. How do I know that? Well, I know that bromine has a high electronegativity, so bromine pulls electron density towards itself. That means that the carbon that is attached to my bromine is going to be partially positively charged, which is going to make it electrophilic. Which means that if I'm going to have some sort of a nucleophile present in the system, I can easily have that species react with said nucleophile. And let's say I'm going to have a thiolate ion as my nucleophile. In this case, the nucleophile going to replace bromine in my molecule, and I'm going to end up with a molecule where instead of a bromine, I'm going to have my sulfur-containing compound SCH3, just like that. So a couple more names that we are going to encounter throughout this video, and of course those are the names that you have already heard before, are going to be the electrophile, and the electrophile is the species that's going to be accepting the electron density. We're also going to have a nucleophile, which is the species that's going to be providing the electron density to make new bond. And finally, we're also going to have a leaving group, which is going to be an ion or a complex group which is going to be departing our molecule during this reaction. While both substitution reactions, SN2 and SN1, lead to the replacement of the leaving group with the nucleophile, they proceed via different mechanism. One of them is going to be a concerted mechanism, while the other one is going to be a stepwise mechanism via the carbocationic intermediate. And we are going to talk about the details of these mechanisms in just a few moments. But before I dive into the mechanisms of each of the individual reactions, let's also briefly review the elimination reaction and what exactly that is. If I take my same starting material that I have in the previous reaction, same 2-bromopentane, and I subject that to different conditions, let's say I'm going to react that with some sort of a base, or I'm going to react it with some sort of polar protic solvent at a high temperature or something like that, then what I'm going to end up with is the formation of a double bond. And the formation of this double bond is going to be a result of my leaving group, which is of course bromine in this case, and the nearby hydrogen being ripped off our molecule in some sort of a way. Just like in the case of SN1 versus SN2, E1 and 2 mechanisms, while both lead to the formation of the double bond, will have different mechanisms. One, the E2 reaction, just like SN2, is going to be a concerted mechanism, while E1 is going to be similar to the SN1 reaction and is going to proceed through the formation of the carbocationic intermediates. So now, let's look at the details of each of those 4 reactions. SN2 reactions. First of all, SN2 stands for the substitution, nucleophilic, bimolecular, and probably one of the most common questions that I hear from my students is what exactly is bimolecular? Does it mean that we have 2 steps there, or what exactly does it entail? Well, bimolecular is the measure of the rate of our reaction. If we look at the rate expression, the SN2 reaction will have rate equals to some sort of rate constant multiplied by the concentration of our substrate. I'm going to abbreviate that as Rx, and we're also going to have the concentration of our nucleophile. And since this is a bimolecular reaction, it means that the rate of the reaction does depend on both concentrations of my substrate and the concentration of my nucleophile, which means that if I increase or decrease the concentration of either of those, or both, the rate is going to change correspondingly. So the number 2 has nothing to do with the number of steps, but it's just the kinetics of this reaction and how exactly reaction rate is affected by the concentrations of our nucleophile and the substrate. So from the mechanistic perspective, as I've mentioned, the SN2 reactions, they are concerted mechanism. So what that means is that if I have my electrophile, in this case, let's take 1-bromobutane, and I'm going to react it with some sort of a nucleophile, let's say it's going to be potassium cyanide, then what's going to happen is that my nucleophile going to attack my electrophilic carbon, and at the same time it's going to displace my leaving group out of the molecule. So think about that as a cylinder with two pistons. When one piston enters the cylinder, it's going to push the other piston out. And in this case, in one step, without any kind of intermediates, we are going to get our product, which is going to be a nitrile in this case, plus my Br- is now floating on its own, and it will find potassium plus as my counter ion. In this reaction, I have created a new bond between carbon and my cyanide, but if I used a different nucleophile, I would have made a bond with something else. SN2 reactions have several important features about them. First of all, there is a stereochemical requirement for the SN2 reaction, and the requirement is that these reactions always proceed via the backside attack, which means that if my leaving group is on a certain face of the molecule, like if let's say I come back to my 2-bromopentane, and in this case bromine is looking at me, the attack by my nucleophile, which in this case is going to be triphenylphosphine, will have to happen from the opposite side. So when that attack happens, my nucleophile that's going to replace my leaving group is now will have to be looking away from me, pH3 over here, just like that, and my Br- as a leaving group is going to be floating around, minding its own business. This is a strict requirement for the SN2 reaction. SN2 reaction always happens with the inversion of stereochemistry. And sometimes this inversion of stereochemistry may be not apparent. Like for instance, in the first case, in the first example that I have here on the screen, my carbon that I have just highlighted in blue did undergo the inversion of the stereochemistry. However, since I have two implicit hydrogens at that position, the inversion of the stereochemistry is not really apparent because, well, the carbon was not chiral, so there is nothing for us to show. But if instead of my hydrogens I had, let's say, one hydrogen and one deuterium, or there was some other substituent on that carbon, we would have to show the inversion of stereochemistry. The second important part about the SN2 reactions is that they are extremely sensitive towards the steric hindrances. The more stuff you have around your electrophilic carbon, the more bulky groups you have around that position, the harder for the nucleophile will be to attack that position. Which means that if I were to rank my electrophiles based on their reactivity in the SN2 reactions, the primary electrophile, something like this, where my leaving group is at the primary position, is going to be the most reactive, followed by the secondary electrophiles, like so, followed by the tertiary electrophiles, something of this sort. And while the SN2 reaction is technically possible in the tertiary position, that reaction is going to be so slow that for any intents and purposes we're going to say that it basically doesn't happen. And I mean seriously, you will graduate before you finish your SN2 reaction on a tertiary carbon. We also want to have good nucleophiles, which typically are going to be small or non-bulky around the nucleophilic atom and ideally negatively charged. So things like cyanide with a negative charge is an ideal nucleophile, but we also can have things with, let's say, sulfur, which is a large atom, although the atom by itself is relatively big. If you don't have much bulkiness around that sulfur, it's going to be an excellent nucleophile. Or different phosphorus containing things. Again, phosphorus has very long orbitals, so it will be very easy for phosphorus to reach our electrophile and make reaction happen. And also we would like to have polar aprotic solvents, so things like DMSO, DMF, THF, DCM, and a bunch of other letters, all of that stuff is going to be good polar aprotic solvents. Typically, instructors have their favorite polar aprotic solvent that you're going to see a lot. However, you can also see a full list in your textbook or in my substitution elimination notes that you can get off my website organicchemistrytutor.com, so feel free to check that one out and get those notes as well. Now, moving on to the SN1 reactions. The SN1 reaction, just like the SN2 reaction, SN1 stands for substitution, nucleophilic, but now reaction is unimolecular, which means that the rate of our reaction is only going to depend on the rate constant and the concentration of our alkyl halide or substrate in general. It doesn't have to be an alkyl halide, it can be other living groups, not just halogens. So that means that the concentration of your nucleophile in this case is going to be completely irrelevant. The only thing that matters to us is going to be the concentration of our starting material, of our substrate, and everything else is not going to affect the rate of our reaction. The important distinction of the SN1 reaction is the fact that the mechanism of this reaction involves the formation of the carbocationic intermediate. So let's say I have this third butyl bromide and I am reacting that molecule with water. Step number 1 in this reaction is going to be my leaving group dissociation. And once I lose my leaving group, I'm going to end up with the corresponding carbocation. Having only 6 electrons around carbon, carbocations are quite unstable and extremely electron hungry, so that is a very powerful electrophile, which means that it's going to grab any electron density we have around, whether it's from the Br- that has just departed or from the water that we have floating around. So if I were to grab Br-, well, I'm going to be going just backwards and it doesn't get me anywhere. But if now I'm going to react with water, then the electrons from water going to move towards my carbocation, which during this nucleophilic attack going to produce a new carbon-oxygen bond. So I have my new carbon-oxygen bond over here. I will show it as a new bond, and because oxygen gave electron density to make that bond, the oxygen is now going to have a positive charge. Be very careful with your formal charges when you are working through those reactions, because if you lose your charge in the mechanism, then you are most likely going to lose points on the exam as well, and few points here, few points there will add up very quickly, so be extremely vigilant about that stuff. Now, the intermediate that I get in this reaction, the protonated alcohol in this case, is not super stable because we have this extra charge on the oxygen, so we want to get rid of that somehow. And the best way to do that, statistically speaking, is going to be with another molecule of water that will float around and pick up that proton in the proton transfer step, which is going to give us our final product looking like this. Third butanol. Now, sometimes instructors and even some textbooks will show that the proton being picked up in the last step is going to be picked up by the Br-. It is perfectly fine to show something like that on the exam, of course if your instructor allows for that, because statistically speaking, the concentration of Br- is going to be significantly smaller than concentration of water, and on top of that, water is actually more basic than Br-. So in this case, saying that it's going to be Br- picking up that proton is a little bit of a white lie, a little bit of a stretch. But for the stoichiometry sake, if we want to say that the co-product that we are getting in this reaction is HBr, and we needed to account somehow for the formation of that HBr, showing Br- picking up your proton is going to be just fine, and in my experience a lot of instructors are fine with that as well. However, I always suggest making sure you double check how exactly your instructor likes to write those reactions, just so you don't lose any points on that little stuff on the exam. So since we are forming the carbocation in this reaction, the stability of your carbocation is going to matter a lot. If you are going to form an extremely unstable carbocation, well, the energy of that species is going to be so high that probably forming that species is going to be, well, next to impossible. So I will remind you real quick that the tertiary carbocations are going to be among the most stable ones. Then we have secondary carbocations that look like this, and then we have primary carbocations where we only have one carbon attached to our C+, and of course we have CH3+, which is a methyl carbocation, doesn't have any other special name or anything of that sort. Now, the important thing that I want to point out here is that the primary carbocations and CH3+ are essentially science fiction. Not that because they don't exist, they do exist, but within the realm of organic chemistry, they are so incredibly unstable that we are not going to be seeing their formation in our regular systems. We're pretty much never going to see the formation of the primary carbocation, not to mention CH3+. So if you're ever tempted to draw CH3+, or a primary carbocation, slap yourself on the wrist because you're doing something very wrong. The only exception from this general rule is when we have resonance stabilization. So most resonance stabilized carbocations are going to be actually more stable than even tertiary carbocations. So if, let's say, I have something like an allylic carbocation, or maybe I have a benzylic carbocation where that plus charge can be redistributed throughout the entire system, those carbocations are incredibly stable and they can be formed relatively easily even if they are primary. And of course, since we are working with carbocations, they come with all possible problems, and one of the biggest problems is going to be rearrangements. When you have a carbocation as an intermediate, always double check for a carbocation rearrangement. If your carbocation can rearrange to give you something more stable, then it absolutely will. But remember, carbocations and molecules in general do not have long-term planning skills. So a carbocation does not know that it's going to become more stable in 3, 4, 5, whatever steps. It only knows if it's going to become more stable immediately. So unless there is an immediate gain in stability, you are not going to have a carbocation rearrangement in that case. Likewise, from the perspective of the stereochemistry, since carbocations are trigonal planar sp2 hybridized species, they're going to wipe clean any kind of stereochemistry that you might have had in your molecule, but only in those places touched by the carbocation. Don't just mindlessly erase all of your stereochemistry from your molecule, only erase the stereochemistry where the carbocation was, and only those positions are going to be affected. And finally, the carbocation formation is typically aided by the presence of the polar protic solvents. So your typical polar protic solvents are going to be things like water, alcohol, and acidic solutions. Next, I want to briefly talk about the E1 reactions. The E1 reactions, those are unimolecular elimination reactions, and they are extremely similar to the SN1 reactions in many cases because, first of all, from the kinetic perspective, the rate of our reaction, just like in the case of the SN1 reaction, is going to only depend on the concentration of our alkyl halide or our substrate in general. Another important thing about the E1 reactions is that they also form the carbocation intermediate, which means that if I start with the same starting material that I had in the previous page and I again react that with water, my step number 1 is going to be the formation of my carbocation via the leaving group dissociation. Once I have formed my carbocation, the next step can be either the nucleophilic attack by water, or, since carbocations don't truly care how they are going to stabilize themselves, they also happen to be extremely acidic, which means that any protons that we have in the nearby position to our carbocation will be able to fly off the shelf as soon as they see anything nearby that can pick them up. So if my water instead acts as a base, then water can come in, pull that proton off, and instead of a substitution reaction, you get yourself an elimination reaction in which we have formed a double bond. So you might ask me a reasonable question. How are we going to determine whether it's going to be an E1 or SN1 reaction if the conditions are exactly the same? Well, they are not exactly the same. One thing that I did not mention here is that the E1 reactions typically happen at the elevated temperature. And higher temperatures will promote the elimination versus the substitution reaction. And that happens because we remember in general chemistry that favorability of any kind of reaction, the delta G, describing the spontaneity of this reaction, is going to depend on the delta H of the reaction minus temperature of the reaction multiplied by change in the entropy of the reaction. So if I look at the elimination reaction, the E1 reaction, I start with third butyl bromide, I react that with water, and my products, I ended up with an alkene. Then I have HBr as my co-product, and turns out that water in this reaction technically acts as a catalyst. It's not being consumed in this reaction, so I'm going to cross it out for the stoichiometry's sake, and I'm going to say that my reaction started with one molecule, but it ended up giving me two molecules, which means that the change in entropy of this reaction is going to be significantly greater than 0. However, in the substitution reaction, if I look at the SN1 reaction and I start with the same third butyl bromide and I react it with same water, my products are going to be the corresponding alcohol over here, and also another co-product is going to be HBr. So water in this case is actually being consumed. So here I'm starting with two molecules and I am finishing with two molecules as well, which means that the change in entropy in this reaction is actually relatively negligible, which means that the higher the temperature gets, the more favorable the elimination reaction becomes. So if I were to plot it on the energy plot like that, I would see that for my substitution reaction, energy changes insignificantly. While for the elimination reaction, my delta G is going to be dropping way faster. And if up to a certain temperature the substitution reaction is more favorable, after a certain temperature the elimination reaction becomes significantly more favorable. What exactly this temperature is? Well, it really depends on each reaction, so we cannot really draw a blanket statement or make a rule of thumb conclusion that at this temperature is going to be substitution, at other temperature is going to be elimination. In reality, both of those processes are going to compete with each other, and you're always going to end up with some elimination and some substitution products regardless of what you do. We're just talking about which one is going to be the major product in each case, and normally we are not going to be giving you exact temperatures, so either we are going to give you no temperature whatsoever, which typically going to mean that we are dealing with the room temperature, or we are going to say that we are applying some heat, which obviously would imply high temperature. And of course, since E1 reactions have essentially the same mechanism as SN1 reactions, you're going to expect all the same things associated with the SN1 reactions to be problems with E1 reactions, namely the loss of the stereochemistry and the carbocation rearrangements on top of that. Also, since the elimination can produce you several different double bonds, you can have double bonds in different positions in your molecule, we are going to use what is known as Zaitsev rule to determine which of the double bonds is going to be the final product as the major product. So if I have a reaction like this, I can have two different products forming either this molecule or I can have another product looking like this. Per Zaitsev rule, we know that the more substituted double bond is generally going to be the major product in these reactions. So if I look at my first bond, my double bond is only connected to two non-hydrogen substituents. But if I look at my double bond on the right side, well, that one is connected to three non-hydrogen substituents. So that one has more substituents, which means that that is going to be our major product in this reaction. Now, the next one in our list is the E2 reaction. This is a bimolecular elimination, and probably the most important feature of bimolecular eliminations that unlike E1 reactions, they are concerted mechanisms, And on top of that, E2 reactions pretty much without exception going to require a presence of a good strong base. So, for example, if I'm going to start with the same tert-butyl bromide like I did for my E1 reaction, if I wanted to do it in E2 style, I need to have some sort of a base. Let's say we are going to take here a sodium butoxide as my base. Now, we are not going to be forming any intermediates here. As I've mentioned, the E2 reaction is a concerted mechanism, which means that my butoxide is going to be using its electron density to tug on the hydrogen next to my leaving group, which is going to cause a cascade of electron density pushing the leaving group out, and that going to produce me my double bond right away without any intermediates. There are a couple of important requirements, however, for E2 reactions, and probably the most important requirement is that the leaving group and the hydrogen that you are trying to eliminate from your reaction must be anti-periplanar to each other, or trans if we are talking about cyclic molecules. What that means that if I construct a Newman projection for some sort of hypothetical molecule, that means that my leaving group and my hydrogen that I'm trying to pull off must be looking in the opposite directions. In the case of a cyclic compound, that means that my hydrogen, let's put hydrogen over here, and my leaving group, they must be trans to each other. If I do not have them anti-periplanar or trans, the molecule either have to be able to flip into the corresponding conformation, or the reaction is going to be so slow that for our purposes we're going to say that it doesn't happen. That means that depending on how your starting material looks like, you would always have to analyze what exactly you have available as a hydrogen to your leaving group, and because of that, certain options, certain products are not actually going to be even an option. What I mean by that is, if I take a classic example that I've seen in probably hundreds of tests, I'm going to have a 6-membered ring with a leaving group, let's say bromine over here, and I'm going to treat that with, I don't know, the potassium propoxide like that. And potassium propoxide is a good base, so we're going to tug on one of the hydrogens nearby to our bromine, and from here we are going to cause the elimination to happen. Now, the important thing here is that my bromine is looking away from me, and I know that the hydrogen must be looking in the opposite direction from the leaving group. So in this particular case, if I analyze all the hydrogens that I have near to my bromine, then I have this green hydrogen that is looking in the same direction. I have the purple hydrogen that is also looking in the same direction, and I have the pink hydrogen which is looking in the opposite direction to my bromine. So the pink hydrogen is the only one that is physically available for my molecule to react with, and all the other ones will never be in the correct conformation to my bromine, which means that I cannot really use any other hydrogen. So here, if I wanted to draw my product, I will have to attack the pink hydrogen. That causes the cascade of the electron density in this way, and the product that I am going to end up making in this reaction is going to be a molecule that looks like this. The other product that you might have thought is going to be our major product, something of this sort, because that is the more substituted double bond, well, that one is not going to happen, because in order to obtain that product we gotta be pulling off the green hydrogen, and the green hydrogen has just the wrong conformation, so it's not available. So that is one of the important things that you are going to be tested on, I can guarantee that. So make sure you always remember to check whether your halogen or leaving group in general and the hydrogen that you are trying to pull off are anti-periplanar to each other or trans. The other thing when it comes to the E2 reactions is, of course, the presence of a strong base. So you gotta know the list of your strong bases. Those are going to be things like LDA, which is not only strong but also incredibly bulky, it is going to be third butoxide, again, strong and bulky, but also you're going to have small bases like amide or ethoxide or other ones. So you got to know your list. And of course, as you have probably noticed by now, I have been adding the links to the substitution and elimination videos that I have dedicated to each mechanism with the practice questions. So all of those links are either over here in the corner, or you can find them in the description below as well. So now when we have refreshed the substitution and elimination reactions in our head, how are we going to predict which kind of a mechanism we are going to see for a reaction when we are not given a mechanism, when we don't know what's going to happen? And that is probably one of my favorite parts in this topic in organic chemistry, and that is the predictive model. Predictive model is a very simple algorithm that, if you follow that, going to give you the correct product and the correct mechanism every single time. So make sure you pay attention to that. And of course, I have a dedicated video on that as well. So step number 1 in the predictive model, the very first thing that you got to do before you start any analysis of your reaction is go ahead and click that like button. Without clicking the like button, the predictive model doesn't work. Step number next, we are going to look at the nature of our reagent. And our reagents can fall into 4 major categories. Our category is going to be the nucleophile only, nucleophile and the base only reagents, and poor base and nucleophiles. So nucleophile only category are things that are excellent nucleophiles but completely non-basic. So those are going to be things like our halides I-, Br-, Cl-, things like cyanide, the sulfur-containing substances, the phosphorus-containing substances. All of those substances are excellent nucleophiles and completely non-basic. Nucleophiles and bases are the substances that can do both. Typically, those are going to be small alkoxides like CH3O- or, let's say, ethoxide, or nitrogen-containing compounds like, let's say, ammonia or primary or secondary amines. Then we have base-only reagents. Those are typically too bulky to be good nucleophiles, but they are also extremely basic, so essentially the only thing that they can do is being a base. Those things are going to be reagents like LDA, or your third butoxide, or things like DBN, or DBU, so those are absolutely non-nucleophilic and extremely basic. And finally, we have our poor bases and nucleophiles. Poor bases and nucleophiles are typically polar product substances like our water, alcohols, and some acids as well. Now, next, once you have established what type of reagent you have, you're going to look at the position of your leaving group. And our leaving group can be either primary, secondary, or tertiary. And that gives us essentially a decision table. We can have our substrate reacting with the nucleophile only. We can have it reacting with a nucleophile / base. We can have it reacting with the base only. And finally, we can react it with poor base and a nucleophile. If we have a primary position nucleophile only, the major mechanism is going to be SN2. For the secondary position, it is also going to be SN2. Since tertiary positions are too crowded for any kind of efficient nucleophilic attack, that is going to be a no reaction type of a deal. Then, nucleophile and the base. At the primary position, the major mechanism is still going to be SN2 with a very minor E2 coproduct. At the secondary position, however, we predominantly going to be seeing E2 with just a little bit of SN2. And at the tertiary position, we are going to exclusively see E2 reactions. Base-only reagents, well, those guys are going to be doing E2 just across the board. regardless of what you are reacting them with. Now, poor bases and the nucleophile at the primary position are typically not really going to do you any good whatsoever, and there will be no good reaction there. At the secondary and tertiary position, we are going to have a mix of SN1 and E1 reaction, and those ones are going to be determined by the temperature of your reaction. If the temperature of your reaction is high, then we are going to predominantly see the E1 reaction. If the temperature is low or room temperature, we are most likely going to be seeing mostly SN1 reaction instead. Then, once you know your mechanism, you can proceed with the reaction and predict the product based on everything that you know about that mechanism. So when you're reviewing for the exam, make sure that you not only know the intricacies of each mechanism, but you're also well versed in the predictive model and can determine which mechanism you're going to be dealing with. And as I've mentioned, I have the links to all dedicated videos about each and every mechanism with practice questions in the description, so if you are rusty on one of those mechanisms, or maybe you want to review all of them, make sure that you go to those links and you check those videos. And of course, you can also go to organicchemistrytutor.com, where I have the full write-up and full tutorials on all of these reactions as well, so you can check that out as well. So what do you think about the substitution and elimination reactions? Do you like them? Do you hate them? Are you indifferent to them? Let me know your thoughts in the comments below, and I will see you in the next video.